I'm Melissa, and this is my presentation about metal nanoparticles effects in fungal diseases. The purpose of the research paper as well as of this presentation is to understand how complex can be diagnose and treat fungal diseases, as well as the importance of an antifungal agent which is able to control outbreaks. The outline of this presentation is going to be first, the introduction, including topics such as the differences among fungi and other microorganisms, fungal outbreaks in the United States of America in the last years, what are biofilms and how they grow. Second, nanoparticles and its size-dependent properties, which are mechanical, optical, and electrical conductivity properties. Third, the antimicrobial effects of metal nanoparticles, specifically of silver and copper, and their modes of action on microorganisms. Fourth, the definition of nanofluids and their optical, magnetic, and dielectric properties. And finally, conclusion. Fungi are everywhere. They are able to live on outdoor surfaces such as soil, plants, and trees, as well as on indoor surfaces including human skin. There are approximately 1.5 million different species of fungi, but only about 300 of those are known to make people sick. These fungal diseases are often caused by fungi that are common in the environment because people can breathe them in or come in contact with them every day. Even though people with weak immune systems are more likely to get a fungal infection, those who have a strong immune system also have a risk, depending on the surrounding they are often in contact with. For instance, medications can lower the body's ability to fight infections. Medical implants in the body are surface for fungi to develop. Agglomeration of people in prisons or hospitals have been blank of fungal disease outbreaks, leading to high mortality rates. So some of the reasons because these diseases are difficult to control is for the need of early recognition, and also because they are able to develop drug resistance. Due to fungal resistance against antifungal agents, the proliferation of the disease is difficult to control, generating outbreaks such as histoplasmosis in an Illinois prison in 2013. The number of cases were 78, was a pulmonary infection and related to disruption of soil contaminated with bird droppings. Another one was the fungal meningitis after contaminated steroid injections in 2012, 751 cases, and was because of contaminated steroid injections from a compounding pharmacy. Another one was the mucormycosis after a natural disaster in 2011, 13 cases, and was a natural environment after the Joplin, Missouri tornado. And other one is the blastomycosis in Wisconsin, 2010-2011, 55 cases, and was a pulmonary infection. Most microbiology investigations have traditionally used free-living planktonic cells in preculture, resulting in the common perception that microorganisms are independent unicellular life forms. However, in their natural ecosystems, most microbes exist as attached communities of cells within an organized biofilm, and rarely as planktonic organisms. As you can see in the image on the left, biofilms start growing as planktonic. Then they form a monolayer and subsequently a multilayer in cells until they get a mushroom form. As you can see, cells starting to detach, reverting to planktonic cells and completing the cycle. These cells are spreading out in the surface and forming more biofilms. Microbial biofilms can form in nature, but also inside a host, such as catheters and other medical devices, in hospitals or inside the body. As you can see in the image on the right, they can form in the mouth and in artificial hip implants inside the body. Additionally, in recent years, it is now estimated that about 65% of all human infections have a biofilm etiology. Based on the antimicrobial behavior demonstrated by metal nanoparticles, as well as their mechanisms of action in microbes, which avoid pathogens' subsequent resistance, they have been postulated as a method to control fungal disease outbreaks. Most of the metal nanoparticle properties are size-dependent. Therefore, they can be tuned considerably by adjusting the size, shape, or extent of agglomeration. One of the most important properties is the large surface area to volume ratio, and that can be explained using this image. The first cube is 1 cm side, so the total surface area is 6 cm square. But if then this cube is divided into small cubes of 1 mm side, the total surface area is going to be 60 cm square. And then is divided into even smaller cubes of 1 nanometer side, the total surface area is going to be much higher, 60 million centimeters square. Other properties of metal nanoparticles are the mechanical, optical, and electrical conductivity properties. Regarding the mechanical properties, they can reach the theoretical values of strength, which are 1 or 2 orders of magnitude higher than bulk materials. The enhancement in mechanical strength is due to the reduced probability of defects. The optical properties can be significantly different from bulk materials. For instance, the optical absorption peak of a semiconductor nanoparticle shifts to a short wavelength due to an increased band gap. The color of metallic nanoparticles may also change with their sizes due to the surface plasmon resonance. Regarding electrical conductivity, this decreases with a nanoscale due to increased surface scattering. However, due to better ordering microstructure, electrical conductivity of nanomaterials could also be enhanced, as occurs in polymeric fibrils. Different types of nanomaterials, such as copper, zinc, titanium, gold, and silver, have come up as antimicrobial agents. Among them, silver nanoparticles are proved to be most effective, and more studies have been performed using them. In this presentation, I'm going to talk about two of those nanoparticles, silver and copper. Silver has a dose-dependent effect, which means that with higher concentrations of silver, the cell mortality rates increase, and smaller particles with larger surface-to-volume ratios have greater antibacterial activity. In the case of copper, it may find potential application as antimicrobial agents, as they can be prepared with extremely high surface areas and unusual crystal morphologies. Additionally, copper is cheaper than silver, but high concentrations are needed to achieve a bactericidal effect. The exact mechanism employed by metal nanoparticles to cause antimicrobial effect is not clearly understood, and is a debated topic among researchers and developers. However, there are various theories that explain the action of metallic nanomaterials on microbes. Focused on silver nanoparticles, the mainly modes of action of nanosilver are described using this image. The circle represents the cell membrane. Inside the circle, there is the cellular content, and outside the circle, the extracellular content. So, the silver nanoparticles can anchor the cell wall and form accumulations or pits, which can cause the membrane disruption, leading to the total release of the cytoplasm content outside the cell and the cell death. Other mechanisms of action occur inside the cell. The silver ions interact with respiratory enzymes, causing the release of reactive oxygen species and causing cell destruction. Additionally, the silver ions are soft acids, and naturally they can interact with soft bases, such as phosphorus and sulfur, which form the DNA. This causes inhibition of signal transduction and the cell death. Moreover, the dephosphorylation of tyrosine of silver ions by silver ions causes the inhibition of signal transduction and the cell death. Metal nanoparticles need a medium to be able to affect microorganisms. After studies performed in the area, fluids came to be a useful medium for metal nanoparticles to interact in. Nanofluids are suspension of nanoparticles in a conventional base fluid, such as water, oils, or glycols. Nanofluids can enhance many of the nanoparticle properties, such as optical, magnetic, and dielectric properties. Regarding the optical properties, nanofluids can be utilized to produce optical filters or lasers. In the case of magnetic properties, they can provide a mechanism for reversibly forming particle agglomerate chains to increase thermal conductivity and control friction between moving parts. Regarding dielectric strength, titanium dioxide nanofluids have been proved to increase the dielectric performance of mineral oil, but studies using aluminum oxide and silica have not been successful, so more studies have to be performed in the area. This is my master research topic, so all the work done by making this presentation and working on the research paper have helped me to position the topic on the biomedical field and to understand much better the previous studies done on metallic nanoparticles. So now I can say that it is evident that metal nanoparticles are able to control the growth of microbes and more specifically of fungi, even in the biofilm state. On the other hand, studies suggest that higher concentrations of specific metallic nanoparticles can cause health problems, as well as environmental disturbance. Therefore, care has to be taken when making experiments, understanding limitations and avoiding any harm to individuals or the environment. I hope studies will be able to find mechanisms to nullify the toxicity of metallic nanoparticles. If this is achieved, the unique properties of these materials would be able to control and avoid fungal outbreaks, as well as be used for human betterment in numerous medical and industrial applications.